Welcome to another exciting adventure in unified robotics here at Lawrence Tech University in Southfield, Michigan. I'm Jim Kearns, and today we're going to talk about the analog inputs that you find on the Atmel AVR chips, specifically the ATmega 128-4P that we use here in the lab. So we'll talk about a little bit about how they work and what they do, and then we'll get down to some example software. The software will be available to anybody watching this, so I'll put a link in the description if you find that interesting at all, just to get you started. I'll tell you up front, it's not the best software in the world, not particularly elegant or anything, but it works and it's give you a jumping off point. Some highlights of the analog input chip itself. There's 8 single-ended channels. What single-ended means is you get the voltage with respect to ground. They have a 10-bit resolution, so you're going to get a 10-bit number, but the absolute accuracy is plus or minus 2 least significant bits. So, you know, those last couple bits are kind of shaky, but that's typical. Nothing to get excited about. The voltage input range is 0 to VCC. In the way we wire the chips here in the lab for our lab controllers, we're using the 5-volt voltage supply for that. You can use some of the inputs in a differential mode, which means that instead of referencing to ground, you essentially have a positive and negative input, and you look at the difference between those two voltages. We're not using that now. I'm not going to talk about it, but it is there if you need it. There are different reference voltages you can choose. There's a couple of internal voltage, or you can use an external voltage like we do. You can leave it free running or just trigger it at a specific time. There's interrupts to trigger a conversion, or interrupts when you can set when the conversion's done. So there's a lot of different things going on there. There's quite a bit of capability in these chips. Now, a couple notes on analog to digital inputs in general. This one uses a successive approximation system, and I will point out I have another video if you really want to go through all the details of analog to digital conversion and vice versa. I'll put a link over here to one of my mechatronics videos that covers the analog to digital hardware in a more generic sense. But this uses an successive approximation A to D, and the way that works is if you have a voltage in and you have essentially a digital to analog converter built inside that A to D system. This whole thing is the A to D. And it has this digital to analog converter which will create a voltage based on a digital number, and then it goes into a comparator. And basically this is a successive approximation. Is just basically a multiple guess. You output a voltage using the D to A converter, and you see if it's too high or low. And if it's high, you guess a lower number from the D to A. Let me write that so you can read it. You guess a lower number, and you just essentially do a binary search until you've found the digital output that brackets this analog voltage input. So that takes time, right? And there's several approximations it goes through. And here it says it's taking 13 to 260 microseconds to do all that. So we have to, this whole thing is controlled by a clock, and we'll get into that in just a minute, okay? There's a sample and hold circuit in here. Basically, if you have your outside voltage, there's a switch, and you go to a capacitor, and then that goes into your A to D like that. So when you want to take a sample, you close the switch, charge up the capacitor, and then when you're ready to, once the capacitor is charged, you open that switch and you can take the reading of that voltage. That has some implications. That's in general a good thing, but it has an implication because of the multiplexing you actually have. If we look over here on the left, I've drawn 4 different inputs here. One of them is connected to voltage, the others are just sitting here. basically what the multiplex means is you can have up to 8 different pins connected in, and you'll close the switch to select one of these at a time. Okay, so let's say we close the switch and we select that first one. The sample and hold is going to close this switch and charge up this capacitor right here. Okay, and then as you that takes just a moment, and then you open that switch, and you can open that switch too. And the A to D converter, the analog to digital converter, your analog input, will now read the voltage across that capacitor. Okay. Now, we want to read the second voltage, so we'll close this switch here, and let's assume that this is just open and there's nothing hooked to it. We close the switch on the sample and hold, and basically that capacitor is connected to nothing on the input, and it's connected to the analog to digital input on this side, but that has a very high impedance. So the capacitor is not going to discharge or change voltages. It's just going to sit there and hold that voltage approximately. So when we open this switch and open that switch, the capacitor still has the same charge on it that it had from that first input. And you're going to read the A to D, and you're going to get the same number that you got before, even though there's nothing connected. And it can continue down for the other switches as you go. So the tendency is, if you have floating inputs, they tend to read the voltage or the last value that you had connected to an actual input. So sometimes you may think that an input's working because the voltage is changing, but it could be just picking up and reacting to something that you read on another channel. So it's just something to be careful about, okay, when you have floating inputs here. Here we have a picture from the data sheet. This has a number of things I want to highlight. Let's take a look at this picture. Over here we have our sources for the analog references. AVCC, which is what we use. There's an AREF input, and there's some internal references which can be 1.1 or 2.5 volts. And those are selected using a couple bits in this AD mux register here. Those bits there will select which of those inputs you're going to use. Other bits in that multiplexer go to the mux decoder, and that essentially picks the actual channel that you're going to use, 0 through 8. Depending on what you have set up, you could also do some differential inputs, but we're not using those. So given this reference, that's the reference voltage for this here is a digital to analog converter. So when that is set to the maximum value, essentially it's going to output that reference voltage. And given an input here, which gets selected through the multiplex and goes through this sample switch here, and it goes up to this comparator. Okay, so now we compare the output of this 10-bit digital to analog converter with the voltage coming in from the analog source, and depending upon if it's higher, you get essentially a high or a low out of that. It goes back to the conversion logic, which then changes the output of that digital to analog converter, and it switches back and forth and does that successive comparisons until you get a final result that gets loaded into these two registers, ADCH and ADCL. It's basically, you have 16 bits there, but 10 of those bits actually contain information, and the top 6 are just empty. Okay. There's a number of other things we have to be careful about here or be aware of. As I said, all this takes time. It takes time for this digital to analog converter to settle to a voltage. It takes time for this comparator to settle. So we have to have a clock that keeps things on pace. What's not shown in here is the CPU clock, but the CPU clock is the master clock for the whole chip. When you get the chip straight from the factory, it's set to be 1 megahertz. You can use the internal oscillator to go as fast as 8 megahertz, and you can use external oscillators to go, I believe, 16 or 32 megahertz. I think it's 16 on this particular chip. And you could even go slower than the 1 megahertz. So the master clock can change speed pretty drastically, but the amount of time it takes for this hardware to settle is relatively constant. So what you want to do is have a clock inside this A to D converter that runs at about the same speed independent of the master clock. And the way they do that is they use this Prescaler register here to take the master clock, which is running at 1 megahertz or 8 megahertz or 10 megahertz or whatever, and divide it and slow down the clock going into this conversion register. Okay. Some interrupt inputs. There's other inputs here to select the type of trigger. These bits here, I think I mentioned in that AD-MUX register, select which of the channels are going. And that's mostly what I want to talk about from this picture. So there's other things going on, but we'll get into that as we get into the software. So speaking of software, here is the header file, and I'll put a link in the description so you can get a copy of this if you want. The way we've set this particular bit of software up is basically it reads all 8 inputs as fast as it can go. So as soon as one value is read, it just triggers the next A to D input, and it just goes around and around and around and around, through all 8 of those inputs. I put some notes on how to use it. Basically, there's a to D underscore init function that will set up all the parameters that we need to get the A to D working properly. The next line there is SEI. Basically, it enables global interrupts. I forget exactly what the acronym says. And the other thing when you're ready to collect data is you just give it this command, get AD val and a channel number from 0 to 7, and it returns the latest A to D values for that particular channel. Okay, so that's some notes I put in the header file. I've updated it since I was doing this, and I also put a note in about that Prescaler. And in the actual code, we check to see if AD underscore H is defined. If it's defined, we just skip all this code because that means we've run this already. These are commands to the compiler to tell it whether to compile this or not. If it's not set, the first thing we do is set it so we don't do a double definition. We create this external variable, which is an unsigned 8-bit integer, and we call it AD complete. That just gets set once when we've gone through that loop once to avoid reading channels that haven't been initialized at all. We have this function A to D init. This is an old function that process A to D. It's commented out here and commented out in the code. You could go back to that if you wanted. That basically just did A to Ds on demand. We have the function here, get AD val, where you send it the channel number and it returns a unsigned 16-bit unsigned integer, okay, with the latest A to D values. And that's all that's in the header file. That just sets it up. And let's go down to our actual sample code. This is the C file. We're including io.h, well, because we're doing a lot of input-output here, and io.h has a lot of things defined for us, like just for example, ADC, SRA, ADPS1, ADPS2, all those things are defined so that we can refer to things by name instead of trying to find absolute addresses, and it makes life much simpler. AVR interrupt, because this whole thing is interrupt driven and we need to define our interrupt vector down below. And of course, A2D lib.h is the header file we saw just above. Okay. So we declare an array, 16 bits of A to D values. Here's that A to D complete that we'll be setting. These two are not actually used, and we could actually remove that from our software. As I said before, this software is not elegant. It's not exceptionally well written. It's just there to get you started and set things up. So let's talk about this A to D init function. We talk about AD mux first. We're taking a value of 1, shifting it left refs0 bits, and setting that bit in AD mux. And our note here is it selects AVCC for analog reference voltage. So if we roll down here, AD mux, and we're looking for refs0, that's this one here, and there's also an refs1. So basically we're going to set these two bits to a 0, 1, okay? And these bits select the voltage reference for the analog to digital converter shown in the table, and I've put, here's that table right here. Since we're 0, 1, we're going to use AVCC as our voltage reference, and the AREF will put a capacitor on it to ground just so it sits there and doesn't do anything, okay? Other options, we could use AREF, we could use internal pins as well. So there's different ways to do it. This is just the way I did it. And these other bits here will tell us which bit is active at any given time. So when we get into the software, we're going to be changing these bits quite a bit, but we want to change these bits without touching those. Next we have ADCSRA. We're doing quite a few things to that. Some of it got separated on different lines. But here we're setting the bits ADPS1 and ADPS2. These go into the Prescaler. We need to get the analog to digital frequency, that internal clock we talked about, somewhere between 50 and 200 kilohertz, okay? And this is giving us a prescale value of 64. So if we're running at 8 megahertz divided by 64, we end up with 128 kilohertz, and that's right in the middle of our range, so that's good. So those two bits down here are the prescale select bits, and here's the table. Depending upon the value, you can divide by 2, 4, or 8, okay? And we're dividing by 8. So we're setting this bit ADIE to enable interrupts at the end of the A to D conversion. Here it is. When this bit is written to 1 and the I bit SREG is set, the ADC conversion complete interrupt is activated. So we're going to trigger an interrupt every time the A to D conversion is complete. We're setting the AD enable bit, so that just enables the A to D to begin with, turns that whole section of the chip on. ADSC, it will kick off that first analog to digital conversion as soon as we go. So we're just going to kick it off and let her rip. So as we go through here, we'll look at this mux stuff a little bit. Again, the lowest 4 bits, mux 4 through mux 0, are these bits. And if those bits are set to 0, 0, 0, 0, 0, we're going to do channel 0, channel 0, 0, 0, 0, 1 is channel 1, 2 is channel 2, 3 is channel 3, and you're seeing a pattern here, and 0, 0, 0, 1, 1, 1 sets us up to the channel 7, okay? Here we get into the actual software. When I call get A to D values and give it a channel number, it just returns the value A to D vals for that particular channel. Doesn't get much simpler than that. So you call that get A to D values, it returns the value, and that's all you really need to worry about in your application software, because all the rest is just going to happen automatically. If you remember what we talked about at the beginning, it is set up, it just reads all 8 channels, starts over, reads all 8, starts over, reads all 8, and it just keeps reading and reading and reading whether you want it or not, and at any time you can just grab a value with this function here. How does it keep reading and reading and reading no matter what? Well, here is the actual software that controls the A to D conversions. Now, if you look at the beginning here, it says ISR ADC underscore vect. ISR stands for Interrupt Service Routine. So this is a routine that's going to service an interrupt when it happens, and the interrupt vector is ADC vect. So anytime this ADC vect interrupt gets set, this is the routine that services it. And in general, you don't want to set up these interrupt vectors and enable them without having an interrupt service routine written, because you set the interrupt, and it goes off to do the routine, and then what does it do? Do we know? Okay. So how this works, reads this parameter ADC low bit from the register ADCL. So it's reading a low bit. I'm going to go all the way back up to the top. We had this ADC data register, which has 16 bits. There's ADCH and ADCL. Okay, those are two 8-bit registers inside this 16-bit register. So the first thing we're going to do when we want to see what is the latest A to D conversion result is we're going to read that register. We'll read the low bit first, ADCL, because when you read that, there's some internal logic here that's not shown. It essentially locks this register so it doesn't get overwritten while you're reading. So you read the low bit and it locks it until you read the high bit. You don't want the high bit changing because it's reading another channel, so it puts a little bit of a hold on things there. You read the low bit from the ADC and it locks the register, and then what we do on the next line is a little more complicated. We have that 16-bit register that contains the result of the A to D conversion. That's divided into two 8-bit registers, ADCH and ADCL. Okay, we read ADCL in that first line. And now what we're going to do is we're going to take ADCH, we're going to shift it left 8 bits, so it lands in the upper 8 bits of this 16-bit register we've defined as ADCHI bit. Okay, ADC with the bad name. So we'll shift it left and land it into the upper part of that. And ADCL, we're just doing a straight OR, so that lands in the lower 8 bits of that register, because we're doing an OR of that low bit and the shifted high bit. So we've essentially populated a 16-bit register here with the A to D results. This bit gets a little bit weird here. I've got my 16-bit number that I want to save, but I need to know what channel I'm on, right? Which A to D channel. And the A to D mux, we had these bits in AD mux that set the channel that we're reading at any particular time. And, the values of that give us the input channel from according to that table. But at the same time, I've got some bits set up right here. In fact, I think it's this bit right here is equal to 1. Okay? So I can't just read that entire register and see what number it is because it's got extra bits set in it. And I want to ignore those bits, and I only want to look at these specific bits right here. And if you recall from my binary arithmetic video, we can do what is called masking. So what I do is this right here, AD mux and 0x07. So that's 7 in hex. If I did that in binary, that's 1 plus 1 is 3. Plus 4 is 7. 0, 0, 0, 0, 0. So when I do an AND with AD mux and 7 hex, I get the results here when I do the AND. That's supposed to be an AND sign. Let me try that again. There we go. The results of my AND, well, whatever this bit here is, doesn't matter, we get a 0. Whatever this bit is, doesn't matter because we got a 0. We got a 0, we got a 0, we got a 0. And these 3 bits here will get either 0 or 1, depending upon whether these are 0s or 1s. Okay? And that essentially is our channel number from here. So the net result here is just the channel number with all the other bits being ignored. So if I'm on channel 2, for example, like I've drawn here, I'll set this in, I'll take this value of ADC high bit, which is our 16-bit result, and put it into the second entry in the array, or array 2. It's the third entry because we start counting from 0. But, slot 2 of A to D vals. So A to D vals ends up being a 8-bit array of these 16-bit numbers. Okay, that's how I get the number stuck in for a specific channel I meant. So the next bit just controls what channel we're on. If ADMUX equals 0x47, I'm cheating here. I'm saying that I know I have this bit set, and if those 3 bits are set, it's 47. That's not a very good way of doing it, really. I should do a masking again and only look at these first 4 values here, actually 5 values. I should really just look at those because, if somebody were to take this software and use it somewhere else and maybe change what we do here, then that number 47 wouldn't work, if you didn't want to do this automatic thing. So that's unelegant, unrobust, and an opportunity for you to think about it and improve it, okay? So we're saying basically if it's equal to 47, we've gone through all 8 channels. So we set ADMUX back to 40, which sets these to 0 and leaves that as a 1, okay? And we set this ADC complete. If this is the first time through the loop, that'll be set. If we've been through the loop before, it's already set, and it's just a wasted operation, but that's okay. Take bit more operations to not do that, I suspect. But basically that just says we've been through the loop at least once. Go ahead and use all the values that you want. But if we're not at 47, the else, we just increment ADMUX. So if we were at 0, 0, 0, we'll go to 0, 0, 1, and then we'll go to 1, 0, and so on. And we'll just keep incrementing till we get back to this 47. So that controls the flow through all 8 channels. If I was only using 2 channels and I wanted them faster and I didn't want to waste time reading a whole bunch of channels I don't need, for example, a quick change I could put right here, instead of making that 47, I could make that 42, okay? Or I could have a register that contains a list of channels that are connected. There's a lot of things we could do here. This is just quick and dirty, get it working, let you use the software, okay? Now we set up ADMUX for the next A to D reading, and we take the ADSC, we take a 1 and shift it over ADSC into ADCSRA to trigger the next A to D. And let's go up and look at it. And that's this bit right here, and it just says start the conversion. So it's just making sure that we trigger the conversion at the next time, okay? So that's it. That's the whole A to D software setup that I've created for you guys to start with, warts and all. Again, the link in the description will tell you where to grab it if you want to grab it just for something to start with. Most of the work is done in this interrupt vector. So in your mainline code, you don't do anything, right? Well, I shouldn't say you don't do anything. All you do in your mainline code is set the A to D init, one time as you're doing the initialization at the beginning of the program. You enable interrupts, and then at any time you want an A to D value for a particular channel, you just call get AD val, and magic happens. So that's it. Thank you for paying attention, I hope, and see you next time. Bye.